Assalamualaikum warahmatullahi wabarakatuh. Welcome back to Siman Laboratory. At the meeting, we will learn about solving case study on an assembly line. The method we will use is the Kilbridge Wester Heuristic method. Before going into calculation, all we have to do is determine the input data from the calculation. The first is predecessor, second is working elements, the third is type. In practice, this time we do data collection as much as 2 times assembly, so we have 2 times that later will be on average to do the calculation. For the first work element of the predecessor strip, the strip is marked as the beginner or the first element to be worked. Work element 2 has a predecessor 1, which means that work element 2 is done after work element 1 is completed. The total time is 24 minutes. And then the input is a product demand. Product demand per day is 32 units. Work hours per day are 8 hours. We turn it into minutes to 480 minutes. If the input has been obtained, then specify the cycle time limit. The formula should be larger than the maximum and smaller than T per day or its text time or time demand. We just set TI max is max, and then plug average time. And then we get the maximum of 5 minutes. For T per day formula is round up work hours per demand product, 0. Okay, in the determining the iteration of the assembly line, you can take the cycle time is between greater equals 5 or smaller equals 15. You can take random values between them to get the cycle time that has the best parameters. In this case study, we are using 3 iterations. The first one takes a maximum of 5 minutes. The second one takes the middle value, and the third one uses 15 minutes or T per day value. The middle value is 5 plus 15 per 2. Okay, then we'll find out which one has the best parameters. First, for 5 minutes iteration, for determining the number of workstation, the formula is round up total time per cycle time, 0. Okay, we will have 5 workstations. The next step is to calculate the cumulative amount wherever the element is at each workstation. First, we take the time on the first element, then the working element 2, the time worked on element 1, plus the time worked on element 2. Okay. And then, if it has reached the limit of 5, so the work element is on 1 workstation. Okay. workstation 1. Then recalculation from the beginning to determine the next workstation. 1 plus 3. Okay. 3 plus 4. No. 2 3 4 5. 2 plus 2 plus 1. Okay, is workstation 4, workstation 5, and workstation 6. Sorry. Okay, if there is a problem with the difference between the actual and the specified workstation, then it cannot be forwarded for the reduction time. So what needs to be changed is the cycle time. To repair it, we're using a 9-minute cycle time. That's still within the cycle time boundary. To determine the number of classes still equal, round up. Total time per cycle time, comma 0. Okay, then you get 3 workstations. If the actual and specified number of workstations are the same, then we can be proceed. Oh, nanti. Cut. Okay, we can calculate cumulative amount. 2 plus 1, 3 plus 2, 5 plus 1, 6 plus 3. It's workstation 1, and then 3 plus 4, workstation 1, workstation 2, 5 plus 2, and then 7 plus 1. Okay. If the actual and specified number of workstations are the same, then we can proceed to the reduction table. How we find the maximum time for our workstation is reduction. How we find the maximum time for all workstation is reduced by the total time on the workstation. Okay, we copy the format 3. Okay, STI max is 9 minus 8, and then square. Then STI max 9 minus 7, and then square. STI max minus STI. Okay. Next to it, we upgrade so iteration calculation are enough to get us here. And then calculating iteration 2 using a 10-minute cycle time. Counting the class in the way, round up. total time per cycle time, not 0, yields 3 classes. Next, cumulate in the same way as before. 2 plus 1, 3 plus 2, 5 plus 1, 6 plus 3. Okay, this is one workstation. Then 3 plus 4, this is workstation 2. And then 5 plus 2, and then 2 plus 1. This is workstation 3. Then proceed with the reduction time, that is, find the highest value on all workstation minus the total time on each workstation, and then square. STI max minus 7, STI max minus 8, 1. Okay, then proceed to iteration 3. We use a 15 minutes cycle time to determine the same class is total time per cycle time, 0, yields 2 classes. Then count the cumulative, then proceed to decrease and square. 2 plus 1, 5 plus 2, 5 plus 1, 5 plus 1, 6 plus 3, 9 plus 3. Okay, this is workstation 1. And then 4 plus 5, 9 plus 2, 11 plus 1. This is workstation 2. And then STI max E square, STI max minus STI. Okay. Then we count the parameters of each iteration. Iteration 1, there's line efficiency, smoothing index, balance delay, and idle time. The formula is line efficiency total time per class multiplied by cycle time times 100%. Okay, then obtained line efficiency first iteration is 89%. And then smoothing index is squared SQRT. Reduction result is okay. The result is 2.24. Okay, and then balance delay is workstation multiplied by cycle time minus total time per workstation multiplied by cycle time times 100%. Okay, the result is 11%. Okay, the last one is idle time. Workstation multiplied by STI max minus total time times 100%. Okay. For iteration 2 and 3, the formula is the same. Just replace the number and adjust it to the iteration. Copy and paste. Okay, we check. This. And then smoothing index. This. Okay, the formula for idle time is workstation multiplied by STI max minus total time. Okay, the result is 3. Index is 0. Balance time. Is workstation multiplied by STI max minus total time. And then the result is 0. The parameters we got were compared to get a good iteration. We have to copy this space value only. And then this. Okay, to determine the best iteration, from the 4 parameters, we do the analysis. The higher the line efficiency of an assembly line, the more efficient it is said to be. The highest is the first iteration. The second one is the lower the smoothing index, the better the assembly line. Smallest on iteration 3. The third parameter is that the smaller of the balance delay, the better the assembly line. The first iteration has the smallest balance delay. Sorry. Okay, and the last one is the lowest idle time rating, and then the assembly line is getting better. Iteration 3 is the best. Okay, we can see the initial purpose of the assembly line, that it to eliminate idle time on each workstation and equalize the time on workstation. So, from the statement, we can conclude that the third iteration is the selected iteration, because the third iterate does not have idle time on every workstation. Why is it only 80%? Because the already specified cycle time does not correspond to the max time of each workstation. If we change the cycle time 12 minutes, then we get a 100% line efficiency value. Okay, then we get iteration 3 is the best iteration for the assembly line. For the last step, we make a precedence diagram based on the best iteration. We need the data of the predecessor, the working elements, to make the diagram and its rotation. Then we get iteration 3, which is the best iteration for assembly line. Okay, we can use draw IO to make the diagram. The first working element as a beginner, then proceeding to work element 2 is performed after working element 1 in the direction of the arrow from 1 to 2, etc. This is 1. And 2. 2, 3, 1, 2, 3, 4, 4, 1, 2, 3, 4, 1, 2, 3, and then 5, and then 6. Okay, if so, this is the first with a total of 12 minutes. Then we set workstation 2 to working element 2 as its predecessor strip, and then working element 2 as its beginning. For the 8 working elements of the 7 working elements, well, for the 9 working elements, it requires or can be assembled when the 1 until 8 working elements are completed. The 10 working elements require the 1 until 9 working elements. Okay, we can name it workstation 1. Workstation 1. Working element 2 as its predecessor strip, and then working element 2 as its beginning, and then working element 8 and then working element 9. Working element 9, it requires or can be assembled when the 1 until 8 working elements are completed. So we can And the work element 10. Work element 10 require the 1 until 9 working elements. Okay. We can name it workstation 2. Okay. So far, the precedence diagram for the base iteration is done and can be in screenshot to put on Excel. From the precedence diagram, we can find out that in the letter assembly, there are 2 workstations and the division of each workstation. The first workstation consists of 6 elements from the elements 1 until 6, and the second workstation is composed of 4 elements from the elements 7 until 10 at the same time. But there is no bottleneck or ideal time. Okay, enough of the material exposure of the Kilbridge Wester Heuristic. Wassalamualaikum warahmatullahi wabarakatuh.